Hello everybody and welcome to my Homework 2 Part 1. Give a quick shout out to the side camera over there. How are you all doing over there? Just kidding, you can see both cameras at the same time. But it would be pretty cool if I edited it, but I probably won't. Anyway, this is Homework 2 of my Comp Methods class. I need to submit this homework as a single playlist with 7 videos, so this will be video 1 of 7. I guess this is part 1A because just make it as confusing as possible. Numerically demonstrate the central limit theorem. So there's a couple things you need to be able to do to numerically demonstrate it. You need to know what the central limit theorem is, and then you need to have some method to numerically demonstrate it. And I'm going to be doing that here in Python. But let's talk about the central limit theorem for a few minutes. What is this? So, as a part of probability theory, the central limit theorem establishes that when you sum up a bunch of independent variables, they will form, like these normalized variables, they'll form normalized variables and make a normal distribution, even though the original variables were not normally distributed. So that begs the question, what is normalization and what is a normal distribution? Well, I think most people who are graduating or soon graduating with a degree in engineering know what a normal distribution is. But I'll go ahead and show you this plot. This is another thing from Wikipedia. And this is just a plot of some normal distributions. So this is basically saying that you have some average value of x, in this case it's 0, and when you have this average value of x, maybe say that's the mean, of a normally distributed set of data, then the data is all going to fall kind of on this bell curve near the mean. And so this x is actually, I believe, a standard deviation away. So a standard deviation is saying that most of the data falls within this range of points, essentially. And so we have the data form this bell curve. And this normal curve, why is it so important? It's because many systems, for I guess whatever reason, tend to follow this set of data when you have random error. If you have error that's just sort of randomly added to a system when you're gathering data, or when you're looking at like real world data, whether you're doing an experiment or just looking at something that totally occurred naturally, you tend to see a lot of normal distributions. It's just a pattern you see in nature. So that's kind of what we're trying to get here, is this normally distributed sum. And yeah, so anyway, if I go over to Paint real quick, I have this up real quick, but let me re-explain this part. So how am I going to do this? I know that I want to make like a normal distribution that looks kind of like this, but how am I going to do this? Well, the central limit theorem says we need a bunch of randomly generated variables that aren't normally distributed. And then once we have these randomly generated variables, we can sum them all up, or we can sum them up in groups, and they can be normally distributed. So what I'm going to do is I am going to go ahead and I'm going to maybe make like a matrix, right? Or an array. And in this array, I'm going to have a bunch of values. So like, we're going to have a bunch of values in this column, or in this row, and then a bunch of values in this row. And that's going to go on for a lot of rows. And then what I'm going to do is I'm going to take this and I'm going to sum up the value from each row. So I'm going to make a new array that's just the sum of, say, row 1, and then similarly the next one would just be the sum of row 2, and I'll just be lazy and turn this 1 into a 2. Look at that, very cool. And then so on and so forth. And so this will be an array with one dimension that's just a sum of all the values in each row. So those would all go to here, and those would all go to here. Now this is actually doing what the normal distribution is talking about. We're going to sum up a bunch of independently generated random variables, and their sums will actually all add up and make a normal distribution, kind of like this. Pretty sweet, right? I think this is all I really need to explain on here for now. And the way I'm going to do all this is in Python. So coming here, let me just go ahead and clear everything out. Sorry, I left a bunch of stuff up. I'll insert a new code cell, and I will actually restart the runtime because I don't want to have anything left over from what I did. I don't want to have any variables or anything like that left over. So sweet. I restarted the runtime, and I need to get like an array of all these values, right, that I talked about earlier in Paint. I need to get an array that looks like this, a bunch of randomly generated values going all the way down. So let's first off start talking about the dimensions of this array. Well, actually, let me go ahead and import numpy, numerical Python, just because it has so many great functions in it. Let's go ahead and talk about these variables real quick. I want to have, say, a number of rows. So I want to have a number of rows. That would be the x sort of value of this array. And that's going to be like the number. So that's going to add up to be what? That's going to be like the number of normal samples. So I'll call that n samples, just because it's kind of hard to write. I'm writing with my mouse, and I'm pretty bad at it. So that's what x would be. But then y, so y would be like the number of columns. That's going to be like the number we want to make normalized. So number per average, if I can spell average correctly. So that's sort of what we're doing here with the number of rows and number of columns, and we're going to sum up each row to get like these normalized values. So I will just go ahead and maybe define the number of samples as, well, how should I define it? I'll say the number, well, actually, no, I don't, that's not a function. The number of samples is going to be, I'm going to use numpy's random function, and then I'm going to tell it to generate me an array. Actually, no, what am I doing? I'm not doing that part yet. I'll just say I want to have maybe 100 samples. And then I'll say the number averaged per sample is going to be, let's just say 10 for now. I think that would be easier. So I have these two constants defined. With that, where's the next place to go? Well, I need to take these two, so I need to make an array with these dimensions, and yeah, randomly generate an array. Unfortunately, what I was trying to do earlier is use numpy's random function, so np.random .uniform. Uniform. And so what this function does is it's from numpy. It's from numpy's sort of random library, or I don't know exactly what you would call that. But this is like the uniform function. So I'm going to give it some dimensions of an array and some bounds. So like, and it's going to give me an array of those dimensions with random values within those bounds. So I'm going to go maybe from -10 to +10. Those are my bounds, and that's the low and the high. Now I need to give it a size. So I'll just go ahead and say size equals, and I'll create a list, I think, if I put in parentheses as a list. And I want it to be, not, well, no, I don't want it to do that. I'll say I want the array to be the number of samples by the number averaged per sample. So now if I go ahead and run that, it should create an array, and sure enough it does, and all the values look to be between 0 and 10. I think all the values are between 0 and 10, so this is pretty sweet. I'll go ahead and define this as maybe samples uniform. Well, yeah, I'll say it's the uniform samples, because once again these are uniformly generated. It's not going to make a normal distribution. But let's go ahead and test that out anyway and demonstrate another function in Python. So from plotly.make subplots, and I capitalized it because I can't type very well. From plotly's make subplots. No, it's I did this wrong, but import. Yeah, so from plotly.subplots, import make subplots. Yeah, awesome. So now I can create a subplot to plot all these uniform samples. So how am I going to go about doing this? Well, I'm going to go ahead and maybe use NumPy has a helpful function. It's called histogram. And so what histogram is going to do is it is going to create a histogram of some values I give it. So if I create it, it'll give me, it wants an array, which an array of the values, and then it wants some stuff about like the number of bins, and then some other things that I don't really need to consider right now. So I'll go ahead and maybe come up here and define a new constant. The number of bins, if I can spell, the number of bins, I'll just say that I want maybe 25 bins, I think will be enough to sort of be able to see it. So the array is just going to be the uniform samples array, and then bins is just going to be n bins, the number of bins. So now if I go ahead and run this, it should return to me 2 arrays. Now one array has a bunch of integers in, and then the other one has a bunch of, one has a, these are integers, and then these are floats, I believe. Yeah, like a list of floats. And so what does each of these mean? Well, I could go through the documentation and explain it, but I'll just go ahead and, I think you can maybe even see it right here. We have this array is the heights each bar in the histogram should be. And then this second array it's giving me is the locations of each of the bins. So what I can do is I can go ahead and save this NP histogram, and I will say that this first array, I will define this first array as heights, H-E-I-G-H-T-S, heights, and then I will define the second array with just a comma, and I'll say the second array I will define as the number of bins. So that's pretty sweet, should work pretty good. I'll get rid of that space there. Now if I go ahead and run this, I have the number of heights and number of bins for the uniform sample generation. So now I can just go ahead and use Plotly's make subplots. So I'll just go ahead and say that a figure is defined as make subplots. That's all you need to do, and I shouldn't have ran that yet. And then so I'm going to go to figure and add a bar to it. That's adding a bar graph, and the x values of that bar graph are going to be the bin dimensions, and then the y values on that bar graph are going to be the heights. So the height of each bar graph, of each bar, is going to go on the y-axis, and the bins are all going to go on an x-axis, like we would expect from a histogram. So if I go ahead and run that, I will get a bunch of data that doesn't look like this, it's just uniformly generated. This is basically showing that when Plotly went through and ran this NP random uniform function, it went from -10 to 10, and it picked a new random point every single time. So it said, one point it was like, oh, I should pick -9. Then the next point it was like, you know what, I'm going to go all the way up to 7, and I'm going to go back down, and do all this sort of stuff. So this data is totally uniformly generated. It's not normally distributed. If I go ahead and run it again, we'll get a new random set of data. I have to run both these cells, but every time you run this uniform, it'll generate a whole new graph too. So I could, go create another one, and you would just see like it all looks like noise. If I created a lot more variables, eventually it would look really flat all the way across. And in fact, let's go ahead and do that. Let's say that I maybe want 1,000 samples and 1,000 average per sample, which would give me a total of 1,000,000 points being looked at here. If I go ahead and run this, it's going to take a minute to plot this 1,000,000 points. But sure enough, you see it's really flat because it's just uniformly distributed from -10 to 10. But of course, as I talked about earlier, in a lot of natural systems, we see data look more like this, where it's normally distributed. So how do I get there? Well, the good news is, the way I set it up, it's not too difficult at all. I'll go ahead and get rid of this chart for now, and let me go ahead and do something very similar, but instead I'm going to take the average of each row, like I talked about earlier, take the average of each row, and then plot the average of all those rows, and see what that distribution looks like. Fortunately, NumPy has a perfect function for this built in, np.mean. So I need to give np.mean an array. Well, that array is just going to be samples, uniform samples. And then I also need to give it an axis to go off of. So if I don't give it an axis, what happens? It just returns me one value. This is saying it took an average of every single value in this uniform samples array. So it took 1,000,000 values, it averaged all of them. Pretty fast for just doing that big of a calculation. Pretty impressive, right? But anyway, I don't want that. I want to average by row. So if I average by row, you would see that you would get like an array with a one-dimensional array. No, it would be two-dimensional. It would be a one-dimensional array, I think. Well, no, I think it would be one-dimensional, just a bunch of values in the array. A zero-dimensional array is a float, I think, if I understand correctly. So that would just be like one value. So you're going to get a one-dimensional array. So what I need to do is I need to say that the axis is going to equal 1. That 1 is just indicating go along the x-axis, or the rows, and average each row. And now, if I go ahead and run this, I should get, yeah, this is the one-dimensional array I'm talking about. So it's trying to show the whole array for some reason. But as you can see, it just goes through and took the average of each 1,000 values. And so it took the average of each 1,000 values and, in each column, and average them into one value for the row, which is exactly what I was trying to do up here. So now I have this array right here. I've gone from this array, which is uniform, and I've gone to a normally distributed array, or at least I've told you it's normally distributed, but let me go ahead and maybe try to prove it to you. So I'll go ahead and define this as samples norm, so the normalized samples. I'll go ahead and define that as that. And then let's copy down all this stuff. And we'll say the heights in bins is just the samples norm divided into n bins, so 25 bins. I'm actually going to, I'll leave it at 1,000 points per sample and see what happens. And then if I run this again, I should get a normal looking distribution. Yeah, and sure enough I do, although there is, it's not perfect, but yeah, look at this. So this is like a normal distribution. Kind of reminds you of the distribution you saw from Wikipedia, the online encyclopedia. But yeah, this is normally distributed. I think I can make it cleaner if I add more points. So let's say I go up to 10,000 samples, and I'm going to average 10,000 points to get each random sample. Then I should eventually, yeah, that's very normal looking. So as you can see, it sort of snakes up and then snakes back down, and yeah, overall, it just looks, it's normally distributed. You can see there's like most of the values fall very close to the average, and as you get further away, there's fewer and fewer values, but you know, there still are values as you get further away. It's not a big flat plot like this one was, if I go ahead and look at a uniform distribution again. So, yeah, in this video I discussed sort of the differences between a uniform and random distribution, and then I numerically demonstrated the central limit theorem. Thank you very much for watching, and I hope you have a wonderful day. Bye-bye.